Welcome to lab class number 11. This is a very interesting lab class because we will be teaching you extremely important signal conditioning unit where you will be looking at lot of interfacing modules, including your amplifier, including your ADC, including your controller, right, and we will be teaching you temperature sensors and how can you how can you design the circuit for this kind of temperature sensor, and we will demonstrate this in the laboratory that we have in my department. So focus on this particular lab class. If you have any questions, feel free to ask, and we have designed particularly this lab class so that you can understand that you can not only use temperature sensor, but you can also use several other kind of sensors if you understand the signal conditioning units, right. So, this will be like a interfacing unit or module between your sensor and your display, right. So, till then you take care. I will see you in next lab class. Any questions, feel free to ask me through the NPTEL forum. Bye.
Welcome to the module. Today we are going to see the design of signal conditioning circuit for the temperature sensor. So, in order to design any signal conditioning circuit, first we should understand the requirements of our system. So, after that we should understand about the complete system requirement. After that we should understand about the characteristics of the input system as well as characteristics of the output system. So, in this case, since our intention was to go with LM35, first let us know the data sheet of LM35. So, when we look into the data sheet of LM35, it provides the information of called sensitivity. So, the sensitivity of temperature sensor is 10 millivolt per degree centigrade. What does it mean? For every 1 degree raise of temperature, it gives an output voltage of 10 millivolts. So, what it means? It means it is basically a semiconductor based temperature sensor where based upon the change in the physical parameter, in this case is the temperature, will be converted into the electrical output voltage, and that electrical output voltage is millivolts in this range. So, the main intention the use of signal conditioning circuit is in order to meet the requirements of the temperature sensor to the next stage, which is our ADC circuit. So, that means if we look into the if I represent the complete system using a block diagram way. So, if I say this is my temperature sensor, so which is LM35, and if I want to interface to ADC, which means another system, we will use some kind of signal conditioning circuit or interfacing circuit in order to meet the requirements of ADC from the temperature sensor. Why do we require? The reason is that when we look into if we directly interface the temperature sensor to the ADC circuit, the accuracy of the complete system will come down. What do you mean by accuracy in this case? Excuse me. So, when we see ADC, if I represent say the reference of ADC is of 10 volts, right. So, and if the bit resolution of ADC is 8-bit resolution, we know that this complete 10 volts will be divided into 256 number of levels. How? That means each level height can be represented with reference voltage divided by 2 power n. So, since n is 8, 2 power 8, which is 10 divided by 256, which is 39 millivolt. So, which means that each level height is of 39 millivolt, and total it will have 256 number of levels. So, if I say the complete system has to be operated within a temperature of 0 degrees to 100 degrees, where this is the region of interest, even though the temperature sensor can go up to -75 degrees centigrade to plus 150 degrees centigrade, but our region of interest is between 0 degrees centigrade to 100 degrees centigrade. So, which means that the temperature sensor without any signal conditioning circuit can provide an output voltage from 0 millivolts to 100 into 1000 10 volts. Sorry, 1000 millivolts, which means 1 volt. So, in order to utilize a complete 100 degree, so this 1 volt will be corresponding to how many number of levels? If we calculate, so each level is of 39 millivolts. So, 1 volt will be correspond to how many number of levels out of 256 number? So, that means 1 divided by 39 milli. So, which means it will use a total of approximately 27 levels. So, out of 256 levels, if we directly interface sensor to ADC, it can only utilize 27 levels. The remaining, so it is not utilizing. So, rather than using that, if I can able to utilize the complete output voltage from the temperature sensor to all the levels of ADC, then the resolution of the ADC or the accuracy of the complete system will be higher. So, what I mean to say is that in this case, if you observe, so the minimum temperature that it can measure is only 39 millivolts. So, what is the corresponding voltage, what is the corresponding physical parameter for 39 millivolts? If we do the calculation, why do we have to do? When we look into the temperature sensor, we will understand the physical parameter, which means in this case is of temperature only by looking or by observing the output voltage that temperature sensor is giving in this case. So, that means, so if the sensitivity is 10 millivolt per degree centigrade, so 39 millivolt will be corresponding to, so 39 divided by 10, which means the resolution of the system is 3.9 degree. So, which is approximately 4 degree. But whereas if I can utilize complete levels, then each level height will be, so if I want to, okay. Whereas if I utilize a complete levels of ADC, so that this complete 1 volt will be divided into 256 levels, will be 256 level, then the accuracy as well as the resolution of the complete system will be higher. But how do we do that? And not only that, when we are designing this particular signal conditioning circuit, the another advantage of going with signal conditioning circuit is that the any mismatch between the temperature sensor and the ADC will be completely minimized by using a signal conditioning circuit. So, the interfacing circuit should always have to have a property of providing proper matching between the output side to the input side of the next circuit. So, because of that reason, we generally we design a signal conditioning circuits using operational amplifiers. Now in this case, the whole idea is that 100 degrees has to be represented with, so that means now in this case if you observe, 0 volts is represented with 0 volts, 100 degree is representing with 1 volt, but whereas if to utilize the complete levels of ADC, if I represent 100 degrees with 10 volts, so whereas 0 degree with 0 volts, my problem would be solved. So that now in previous case only 27 levels were utilizing, whereas if we have 10 volts as an output for 100 degree, all the levels will be utilized. So, that means what is the resolution of temperature sensor right now, of the complete system right now? So, one thing is that, so if we calculate, if we do the recalculation of the utilization of the resolution of a complete system, so 10 volts is represented with 100 degrees centigrade, and now I am getting 39 millivolts. So, which means that 39 into 100 divided by 10, so which is 390 millivolts. If the temperature sensor has a resolution of 0.39 degrees centigrade, then the complete system can give the change in the input temperature for every 0.39 degrees centigrade, which is less than 0.5 degrees centigrade. But whereas if we are not using this signal conditioning circuit, if we are not using this particular signal conditioning circuit, then the resolution of the system is 3.9 degrees centigrade. So, one thing it is clearly understood that using a signal conditioning circuit can achieve the best accuracy as well as the resolution of the complete circuit. You may ask, will it be not useful if you go with a higher bit ADC? Yes, it can also be achieved with even higher bit ADC, but the problem with higher bit ADCs is that cost. So, one way with a low cost by using a simple operational amplifier between the output and the input side of an ADC can utilize or can achieve higher resolution. Now, so it is clear why we are going with signal conditioning. Now, next thing we will see how can we implement such a system to get 100 degrees with 10 volts. So, in order to understand that, let us calculate the gain factor. So, now let us see how can we implement such kind of signal conditioning circuit using operational amplifier. So, before implementing it, let us calculate what is the logic behind in order to convert that 100 degree centigrade or the output from the 100 degree centigrade to the to the input of ADC. So, which means that in our case 0 degree to 100 degrees is the region of interest or the operating range that we are looking for developing a system. So, we are getting an output from generally we get an output of 0 millivolt to 1 volt, but whereas if we can implement from 0 to 10 volts, then the resolution of the system will be higher. The minimum change that it can record is of 0.39 degree centigrade. However, provided our temperature sensor should change or provide an output signal for a change of 0.39 degree centigrade. Okay. Now, so that means 1 volt I should convert into 10 volts. So, output is 10 if the input is 1, and this is completely linear, even this is completely linear. So, whenever there is a change, it will also output also has to change at the same factor. But what is that factor which has to be provided to the system or the interfacing circuit such that any change in the input should change by that. So, that means if I want to do that, we can say output by input, which is nothing but gain 10. So, that means if I have a temperature sensor, which in this case is of LM35, and if I provide a gain amplifier with a gain of 10, give it as an input of ADC, my problem is solved, so that it utilizes all the levels of ADC. Or even if you do not have an ADC, we can easily visualize the effect of having a gain of 10 into the system. So, how can we utilize? In a previous case, if you do not have it, so we are by looking into the output, say if I get 1 volt, which means that we can understand the temperature sensor of 10 volts. But in this case, how it will be represented? It will be represented 10 volts, which means that if I say 10 volts, I am getting output of 100 degree, means the physical parameter or physical interest is of 100 degree, the temperature is 100 degree in this case. If we are measuring 1 volt, which means that we are getting 10 degree centigrade, right? Whereas if the output is 0, which means that the output is also 0, the input is also 0 degree. So, understanding this is very easy with a higher gain, lower the higher the signal to noise ratio. So, everything will will be easy. Now, how can we implement it? So, there are different ways of doing it. Either we can go with the inverting amplifier or non-inverting amplifier configuration. But we will see one by one implementation of gain of 10 with inverting amplifier as well as non-inverting amplifier too. So, the goal of this is implementation of amplifier with a gain 10. So, if you recall the working of, so this can be done in two ways. One, by using inverting configuration, and other one is non-inverting configuration using operational amplifiers. So, in case of inverting configuration, So we'll use an inverting amplifier. If you recall the connections of inverting amplifier, so we will be always provided plus 15 one side and minus 15 another side. These are the operating voltages of an op amp, so that the saturation voltage of the output of the operational amplifier entirely depends upon what is our plus VCC and minus VCC, and it will also contain, as you remember, if you recall, it will always have three terminals. One terminal is for the input, which is a negative terminal, which is nothing but a inverting terminal. The other terminal is a positive, which is a non-inverting terminal. Other one is an output. So in case of inverting amplifier configuration, since it is an amplifier, we should always have to have a negative feedback, and the positive terminal should be connected to the ground, and we will also have another resistor which is connected. So if this is input, if this is output V0 I am representing, and if I say this as RF and this is R1, the gain, the output voltage of the inverting amplifier is minus RF by R1 into Vin. Right. So since in our case we require to have a gain of 10, so that means V0 by Vin should be 10. So which means that RF by R1 should be 10. So if I say RF is equal to 10 R1, if R1 is 1K, then if I consider RF as 10 kilo ohms, my problem solved, I will get a gain of 10. But the problem, or in this case what is the problem is that since it is an inverting op amp configuration, the output voltage and will always be out of phase with Vin. So if you provide a positive input voltage, you will get an output as negative. If that is okay, then we can go with. But in our case, if the next stage has a reference of 0 to 10 volts where it cannot accept the negative signal, then I have to change the phase from negative to the positive. So in order to do that, what we do is that we will take another operational amplifier with a gain of 1, but even in this case we have to go with same inverting operational amplifier. So in this case I will take 10K or 1K 1K. So now if both RF and R1 are same resistance, we will get RF by R1 as 1. So V0 will be followed by Vin. Sorry. So as a result, even though if for 100 degrees centigrade, if this is giving minus 10 volt, here we will get output as 10 volt. So that we could able to achieve 10 volts for 100 degrees, but this is by using inverting operational amplifier configuration. So we will be using two operational amplifiers. So whereas in case of a non-inverting amplifier configuration, if you recall the working of non-inverting amplifier, so RF, R1, say this is Vin, so V0 is equal to 1 plus RF by R1 into Vin. So now in this case, if I calculate, if I want to know what is the values of RF and R1, so we should substitute our required gain. So we will get RF is equal to 9 times of R1. So if we can consider a resistance of RF and R1 in this fashion, we can understand, we can get a gain of 10. But the only problem is that finding out the exact resistance of R1 and RF in order to get a required gain is little challenging. But you can use a potentiometers even to get the same resistance. But in this case, if I consider R1 as 120 ohms, so if I say R1 as 120 ohm, so that RF will be 9 times of 120, the value will be 1.08 K. Hmm, 120 into 9. So 1.08 K. But finding 1.08 K is different. So closely associated resistance is 1 kilo. So if I use 1 kilo ohm and 120, we will get again a close to 10. So, but in case of a non-inverting amplifier, with a single operational amplifier, we could achieve the same gain as 10, right. So, just remember the input should be connected to the inverting terminal in case of inverting configuration using R1 resistance, whereas in case of non-inverting amplifier, we will be directly interfacing to positive terminal of operational amplifier. Now, we will see the implementation of both inverting amplifier as well as non-inverting amplifier for a gain of 10 using our TA board. Then we will understand the working of each system. Then I will interface LM35 temperature sensor to this, and by looking into the output voltage, we can understand what is the system temperature at present. Okay. Let us see about the working using the board. So, now we will see the connections of what we have discussed previously using the implementation of inverting amplifier as well as a non-inverting amplifier for a gain of 10 using our TA board. So, if you look into our TA board, it is analog system lab kit pro. So, it contains different subsystems. So, here on the bottom side, if we observe, there are 3 different variants of operational amplifier. So, first variant, what they call it as op-amp type 1 inverting, where it along with the operational amplifier, which is in this case is a dual operational amplifier, it has different resistances as well as a capacitances. So, any configuration that we want to implement can be easily implemented using this using any type of subsystems at this point. So, there is another thing, op-amp type 2 full, it also contains a different resistance as well as a different capacitances. When we are going with say for example filter configuration, so we can use either op-amp 1 and op-amp 2. But the challenging part here would be, so it is fixed with different fixed number of resistances. However, in case if we want to use extra resistances or the resistances and capacitances which are not available on the board, by using the breadboard and by using the jumper connections, we can simply connect it from the breadboard to the operational amplifier side. Along with these 2 other type of op-amp subsystem, which is op-amp type 3 basic, where it has only the connections of input output connections without any resistances and capacitances. So like the basic design can be completely implemented, but any resistance or any passive elements that you have to use has to be connected using this. So if you carefully look at this is the IC, which is a TL072, which is a dual op-amp. So since it is very difficult to understand the configurations directly, the negative terminal has been connected with the 4 buck connectors, positive terminal, non-inverting terminal also been provided with the 4 positive 4 buck connectors, and also has a separate pins for the ground and a 10 volts power supply. If we want to provide single power only to the board, this particular subsystem at this point we can do. Or there is also option where by using a main power, by providing plus 10 plus minus 10 on the ground, we can either access the powers using this board, or it can directly internally it has been already routed for connections from this to powering all the operational amplifiers as well as other circuits available in the board. So in order to tap the output voltages, again they have provided with the buck connectors. So now what we do is that we will use this particular configuration, either this or this, and we will implement both inverting amplifier configuration, non-inverting amplifier configuration. We will see whether the design circuit is giving a gain of 10. How do we test it? We will be applying a known input voltage, we will measure the output voltage, and the difference output by input gives the gain of the complete system. By looking into that, we will see whether we have achieved the targeted gain as well as a practical gain or not. What I mean, the practical gain and the targeted gain are same or not. So if you carefully look into that, along with this other type of operational amplifier, other type of subsystem, this type of subsystem, it also has other type of subsystems like analog multipliers. It also has diodes, where if I want to use a particular diodes, you have an option where you can directly connect and you can tap by using these buck connectors. It also provided with trimmers in case if it is required. Along with that, it also has a DC-DC converter, provision for placing a transistors, LDO regulators too. and they have also given with digital to analog conversion. So, instead of using a breadboard and connecting all the ICs on the breadboard and use the wires to do that, by using simple jumpers, whatever the design that you require to do, we can use using this board with a minimal effort. Okay. So, now let us see the implementation or the connections of implementing both inverting amplifier configuration and non-inverting. So, let me go with inverting amplifier configuration. So, in order to provide a gain of 10, if you recall the circuit that we have used, we require a feedback resistance of 10 times of the input resistance. So, I will take input resistance of 1 kilo, so that feedback resistance I go with 10 kilo. Right. So, let me take few jumpers in order to do the connections. So, if you observe here, what we require, the input has to be provided from 1K. So, if you carefully see to the inverting terminal, one end is connected to OPA 2A in. So, OPA 2A indicates this is the second subsystem on the operational type. A indicates, since it is a dual op amp, it has divided with A and B. Channel A indicates the first operational amplifier, B indicates other operational amplifier. Excuse me. So, to the negative terminal, along with that, it has provided with fixed resistances. The resistance they have given was 1K, 2.2K, 10K, 4.7K and 1K. Whereas, the other end of the resistance, if you notice, it is connected to the buck connectors. Similarly, output side if I see, it has provided with a buck connector. So, what I will do is that, since the input has to be connected to the R1 resistance, so I will take a jumper and input resistance should be 1K. So, input I will be providing at this terminal. So, that means to the input one end of the resistors it is provided with, it will be providing with the input, whereas the other end is directly connected to the negative terminal. Whereas we require a feedback resistance of 10K. So, in this case, the third resistor is a feedback resistor, where the feedback resistor should be connected between the negative terminal and the output. So, since one end of the resistor is connected to the negative terminal, so simply by using another jumper connecting at the other side of the resistance to the output shows the connection for feedback. So, that means now I have given connections for both input as well as an output feedback resistance. But the positive terminal, which is a non-inverting terminal, should be connected to the ground. So, what I will do is that I will take the positive terminal. If you notice, it is also having a ground buck connectors. So, if I simply connect it between the ground and IN plus, which means that the positive terminal is connected to the ground. So, now I make the connections of first operational amplifier. Let us see the working of it. So, in order to understand the test, the working and the gain of this operational amplifier, we have to provide a power supply. The power supply will be connected to this. So, since here it is grounded, which means that this and this grounds are same, internally shorted. Whereas, the positive terminal plus 10 and minus 10, whatever you notice is here, if you connect a power to this, automatically the power to all the operational amplifiers will be provided using internal wiring, right. So, let me connect the raw power to the main power, let me connect the output from the linear power supply DC source to this particular connectors, and we will provide an input known signal at this point, and we will observe what is the output we are getting. Then we will calculate output by input in order to understand the gain. Let us see the connections. So, what we have made, the power supply, the DC linear power supply that we have has a dedicated power source for plus 15, minus 15 and ground. So, we have connected the plus 15 to the main power one side, which is the positive terminal. Even though the board shows plus 10, minus 10, we have connected with 15 because the operational amplifiers can withstand up to plus or minus 18 volts. So, that is why, since we have a dedicated power supply for 18, we have directly connected it, and for a negative, the green wire has been connected to the other side, and the ground, which is a common terminal in this case, is connected. So since we have to provide a known input to the system, we are taking the first channel in the regulated DC power supply. So the positive terminal at this point is connected to this 1K input 1K resistor, to the input side of 1K resistor. Along with this, in order to visualize and in order to see the input and output responses, it is connected to the first channel of CRO. Similarly, to visualize the output voltage to the second channel of CRO, DSO in this case, we have connected the output terminal to this. The grounds are common, which is commonly connected. Now, let me switch on. Right. So, let us understand the working of, let us see by varying the input voltage, what is the output that we are getting it. So, now in this case, yellow represents, so we have two channels. This yellow represents input side. So, whatever the input is being provided to the positive terminal of operational amplifier, sorry, to the resistor, input of a resistor, output indicates output from the blue indicates output from the operational amplifier. So, since the power is 0, the input voltage is 0 in this case, so the output and input are simply 0. So, if you observe carefully, the vertical one box represents 500 millivolts, whereas for the blue one box represents 2 volts. Since a gain of 10, so if we provide 100 millivolts as an input to the system, we will get approximately of 100 into 10, 1 volt. So, but this is not the right way. Since we are testing our inverting amplifier configuration, we will provide the known input and we will measure the output side. Right. So, let me provide the input voltage. So, I am giving the input of 100 milli. So, here if you observe the mean value, it is approximately 100 millivolts, the maximum is 160, whereas if you observe the output of 1.31 volt. Okay. So, let me zoom in little bit. So, I will change both is of 200 milli and 2 volts. So, easy for us to understand. Fine. So, let me change it to 100 milli. So, now if you see, we have provided a mean of 103 millivolts, we are getting a mean of minus 1.06 volts. So, which is at 10 times, approximately of around 10 times. So, let me go with another voltage, which is of a mean of 200 milli, and let us see how much we are getting it. So, here if you observe, the mean of input is of 193 millivolt, we are getting close to the mean of minus 2.1. So, if you observe carefully, the output voltage, input is a positive, but the output we are getting in the negative, which indicates that because of inverting amplifier configuration, we will always have a phase, a difference in the phase. Magnitude will be 10 times of the input, but the phase will always be different. That is because of our inverting type of amplifier. However, if you realize our circuit, along with this one stage of inverting amplifier configuration, again we have to go with other stage of inverting amplifier configuration, then we have to observe it. But before that, let's just have a look. Then I will go with somewhere around 500 milli. So we can see applied input voltage of 498 milli, we are getting minus 4.91, which is also close to 10. Then just go with 600. So applied input of mean value of 5.94 milli, we are getting a minus 5.92 volt, which is also close to 10, right. So from this it is clear that as we are keep on increasing the voltage, so just go with 1 volt, we should get an output of 10, provided we cannot go more than 1.2 or 1.3 volts, because if you go more than 1.2 1.3, then the output voltage, since the gain is of 10, it will go to 12 to 13 volts. Since the plus VCs and minus VCs of operational amplifier here is provided is of 15, so above the saturation voltage, whatever may be the output, it cannot be represented. So the maximum output voltage the op amp can can show is only till the saturation. That saturation entirely depends upon the power supplies being provided for operational amplifiers. So now if you observe, I am giving with the 1 volt. Let's see what do I get it when I give an input of 1 volt, right. So I have provided input of 1.04, I am getting output of 10.2. So from this it is clearly see that, so it is having a gain which is close to 10. So 10 point something, but which is very close to 10, but the magnitudes are same, but there is a phase. So in order to correct the phase, what we do is that we will use another stage which is also inverting amplifier configuration with a gain of 1. Let's see how exactly I am doing the inverting amplifier configuration with a gain of 2. So now what we will do, since we have to realize another stage, which is by using inverting amplifier configuration with a gain of 1, I will use this particular stage, which is OP2B. Even in this case, we have a dedicated jumpers for negative terminal, positive terminal, as well as an output. Also, the board has been provided with different resistances, but in this case, since we require a gain of 1, the input resistance should always be equal to the feedback resistance. So what I do, I will take another jumpers and connect. So since we require input, I am using RF as well as R1 resistance as 1K. The first resistance, if I see, it is 1K. So one end of the resistor, I am connecting it to the output side of an operational amplifier, whereas other end it is directly connected to the negative terminal. So I don't have to do any connections. Since we require a gain of 1, the bottom resistor is also 1K resistor. I will take another jumper. I will connect one side of the resistor, which are connected to the jumpers. Is it okay? It has changed. Okay, right? Since one end is directly connected to the negative terminal, other end of the resistor I am connecting it to the output. So output in this case is this. So my connections are done, but I have to observe the output from the output of the second stage. So what I have done, the CRO probe, second channel of CRO probe is connected to this. So if you recall, the output of the first stage anyway have been provided with to the input of 1K resistor, and the feedback resistance, which is also another 1K, is connected to the output, but we have not provided the positive terminal to ground. So I will take another jumper, I will connect this particular positive terminal to ground. So my connections are done. Again, so I have not changed the connections to to the first channel of CRO as well as second channel of CRO. So just have a look on to the CRO now. We will observe by varying the input voltages from 100, 200 till 1 volt, we will observe what is the output voltage. Now we will also observe along with the magnitude of output voltage whether we are getting a positive magnitude or a negative magnitude, which is reverse of the input phase what we have connected it. So in order to understand that, let me okay, if you observe again the blue represents sky blue represents the output and yellow represents our input. Let me keep both the things to the same stage. So now I will apply input of 100 milli. So here if you apply input applied is of 107 milli, we are getting output of 1.04 volts, but when you see the phase of both the things which are positive. Next I will go with 500 milli. So one box corresponding to the 500 milli for yellow. So when I see slightly I have to increase. Right. Input applied is of 503 milli, 504 milli, output we are getting of 4.96. So which is also close to 10, gain of 10, but same magnitude, same phase. I will go with 1 volt. I am also changing the scale of it. So even 5 volts scale. So if you observe input applied is of 1.04, 1.04, output we are getting 10.3 volt, which means that the gain is now 10 and the phase is also same. So with this we can clearly see that we could able to provide or we could able to design the gain of 10 amplifier, right, using inverting amplifier. Now what we do is that here we have LM35 temperature sensor. LM35 temperature sensor, we will connect the output of this LM35 temperature sensor to the board, and we will observe what is the output voltage we are getting from the complete system. Since in order to understand what is the temperature of any system, so we should by looking into the output voltage we can easily do that. How can we do? So since we do not have any heating source, we will use a soldering station which will be always heated to some particular temperature. We will measure that, we will understand by looking into the output voltage of the system at what temperature that heating station is at. So in order to do that, first we should understand about the terminal configuration of this LM35. If you observe this, when we are facing towards the flat side of LM35, we can see the 3 terminals. So the first terminal is nothing but positive terminal, which is plus 5 volts we have to apply. The extreme on the right side, extreme is the ground terminal, reference terminal. The output will be from the center terminal. So what I will do, since maroon, brown and white, maroon will apply 5 volts to the maroon. To the brown will connect it to the inverting amplifier, input side, and to the white we will connect it to the ground. So let me connect it, then we will use a heating station and we will observe whether we are getting any changes in the temperature, or we could able to measure the temperature of heating station. Now if you see the connections, so what we have done is replace the input side of the operational amplifier with LM35 temperature sensor. So if you see the connections of LM35, the input is connected to the 5 volts, the output is connected to the input side of inverting amplifier to the resistance of inverting, first stage of inverting amplifier, whereas the ground terminal is connected to the ground, and the output again can be measured by using this particular CRO probe. Now when we look into the output, when we look into the oscilloscope, here we can see that the mean value represents 2.87 volts. So now if you recall the complete working of the system, we know that the gain of the system is 10, and by looking into the output voltage, if we understand, since it is not connected to any plant right now, which means that it is at room temperature. The room temperature is around 28.1 degrees centigrade. How can we say? The reason is that when we look into the sensitivity of the temperature sensor, 10 millivolt per degree centigrade, 1 degree will be always represented with 10 millivolt. Since we have a gain of 10, 1 degree will be represented with 100 millivolts. But now I got 2.8 volt, which means that it is corresponding to 28.1 degree centigrade. So which is also compared to the room temperature, it is also same. Now in order to understand the testing of this one, what we do is that we use this soldering station. So I will connect the temperature sensor to the soldering station. Let us see whether there is a change in the temperature or not. If you see, the temperature started increasing, right now it is at 9.7, 10.3, 10.7, which has been stopped at 10.7, which means that the soldering station, this particular soldering rod, the temperature of this soldering rod is 10.7 volts it is showing, which means that it is at 100.7 degrees centigrade. Right? When I remove the temperature sensor, so it starts cooling. Let it start cooling. So started decreasing. So right now it is at room temperature. So since it is previously heated, it takes some time to again cool it down. Little temperature on this. So if I touch it, it cools very fast. So here we can see again it is coming down. So with this we can understand that we can use this particular temperature sensor, and by looking into the output voltage we can easily understand the output voltage, the temperature of the plant. Now we will try to realize the same circuit the same way, whatever we have done for the inverting amplifier configuration, we will also try to implement the same by using non-inverting amplifier configuration too. Now see how can we implement the non-inverting amplifier configuration at this stage. So in case of a non-inverting amplifier configuration, we can only use one operational amplifier where the input should be connected to the positive terminal, and the feedback resistance as well as the input resistance, other end of the input resistance should be connected to the ground. Since we require the gain of 10, we have seen the resistance that we require in order to implement for a gain of 10. So what resistances we require? We require 120 ohm resistance as input and 1K resistance as feedback resistance. So let me take 120 ohm resistance. So since here we are connecting external resistor, what I will be doing is that I will use this breadboard. I am connecting this 120 ohm resistance to the breadboard. and one end of this should be connected to the ground. So, I will take this terminal, I will connect it to the common ground, whereas another end should be connected to the negative terminal of an operational amplifier. So, I will take another jumper, from here connecting it to the negative terminal. So, input resistance is connected. Next, what is the feedback resistance? So, in order to connect a feedback resistance, if you remember, we require a feedback resistance of 1.08. The closest resistor which is available is 1 kilo, and that 1 kilo is already there here. So, if I consider the top 1 kilo, if you see that one terminal is already connected to the negative terminal, whereas other end of the resistor I will use it is connected to the buck connector. So, what I will do is that I will use the other end of the resistor connected to the output terminal, which means that the feedback resistance is also connected. Now, what the input should be connected to the positive terminal. So, what I will do, I will take so the positive terminal, I will connect it to our DC power supply. So, if you see one terminal, one channel from the power supply connected to the positive terminal. So, since we have to understand the output voltage, what I will do is that the second channel of CRO I am connecting it to the output. So, whereas the negative terminal should always be connected to the ground. So, since I have a ground terminal here, I am connecting it there. Then in order to do the comparison between an input and output, and the difference that the output by input gives the gain of it. So, let us to understand what is the input we have provided, what I will do is that I will use the first channel of CRO will be connected to the positive the input of operational amplifier, positive terminal of op amp, whereas the other the black pin, which is a ground pin, is connected to the same ground. So, with this we finished our connections. Let us see the working of the board. Right. So, let us focus on the oscilloscope. We will try to increase the input voltage with the steps of with 100 milli, 200 milli, 500 milli and 1 volt, the same way whatever we have seen the previously in inverting amplifier configuration, and we will observe how the output is also changing. So, the output by input gives you the gain, and we will calculate the gain. So, let me increase the input voltage. If you observe, I have given an input of approximately 300 milli, 296 millivolt, but I am getting an output of 2.8. When I do the calculation, 295 milli, 2.8 divided by 295 milli. So, the gain is of 9.49, 9.5. The difference is because of we do not have an actual resistance of 1.08 K. There will be a slight deviation from the gain. However, but on a bigger picture, if you observe, the gain is almost equal to 10. Then I will change it to 500 milli. So, if you observe, I have applied input of 485, 491, 493, 500. So, I applied around approximately of 500 millivolts, I am getting 4.67 volt. So, let us go with 1 volt. It should generally get 10 volts, but we will get close to 10, which is somewhere around 9.5. Right. So, when you apply input of 1 volt, we are getting output of 9.36 volt. So, with this we can understand that there will be always the selection of a resistance with a non-inverting amplifier configuration is little tricky, like tricky in the sense availability of the resistors close to the required gain. However, since the input is directly connecting to the positive terminal, the input impedance of the complete system is equal to the input impedance of an operational amplifier, which is very, very high. But however, if you see that it is following as per our required way, or the gain is always is almost close to a 10. Now, what we do is that we will remove the connections of input side, we will interface it to LM35 temperature sensor. We will perform the same experiment as what we have seen previously. Now, if you see the connections, what I have done is I replace the input from power supply to the input to non-inverting terminal, replace with output of the temperature sensor now has been connected to the input of non-inverting terminal. Since LM35 requires some power input voltage, that 5 volts has been provided from the first channel of power supply. So, in order to understand the actual temperature right now, so the output from the complete stage been connected to the second channel of CRO. So, if you recall what was the temperature, room temperature that we measured, it was around close to 28 degree. Now, if you see that the mean value, it is showing it as 2.6 volt. So, previously it was 2.8, now it is 2.6. The difference is because of the gain, the difference in the gain. But however, there is error of 2 degree, but let us observe by connecting the working of this LM35 or by connecting it by just connecting it to or probing touching it to the soldering station, whether we get the same temperature or not. So, just I connected it. Can see it, right? You see it, it started heating. Closely it has come to 10.9, 11.2, 11.4, right, 11.8. So, now the heating station has heated to little high temperature. The maximum voltage it is showing it of 12 volts, which means that it is right now at if we consider the gain of 10, it is at 120 degrees centigrade. So, now I have removed the connection, it will start slowly coming down because of convective cooling, come to the room temperature. So, with this we can see the working of a temperature sensor, as well as we can also understand how can we interface a temperature sensor to the signal conditioning circuit, which will meet the requirements of our ADC or any other stage that we are connecting, and at the same time the implementation of amplifier, which is an inverting amplifier as well as a non-inverting amplifier configuration for a gain of 10, right. So, with this I hope it is clear the working of temperature sensor as well as the signal conditioning circuit and its importance when we are interfacing it to our any kind of ADCs. Thank you.